So we have a few objectives today with scale diagrams. The first thing we want to be able to do is just basically learn how to use one. And we'd like to be able to use it for both an enlargement problem and a reduction problem. So a reduction problem means that what you're seeing has been reduced. So for example, if we're looking at a scale diagram of the city of Surrey, then that's obviously been reduced to fit on a piece of paper because you can't fit the whole city onto a piece of paper. But if you're looking at something like, say, a scale diagram of, I don't know, maybe it's a, like a cell in biology, then that's obviously been enlarged to be fit on the paper because you can't see it unless it was, enlarged. The other thing we're going to want to do is be able to figure out the scale figure out the scale of a diagram. So I'll show you an example with some maps I took for Google Earth. So pyramids in Giza. I don't know if I'm assuming everybody's heard of these. Okay, so it's hard to see, so I've expanded what the scale is. But basically, when you look on Google Earth or Google Maps, you get these bars, and on the top it's saying that this much distance is equivalent to 50 meters, and it also gives you a measurement in imperial, like feet. So the bottom one here, that is 200 feet. So even though you're looking at, a very small picture, it tells you what the actual scale would be. So what you need is a ruler then in order to figure out the actual sizes of the diagram. So when I measure off the on my screen here, I get that this is 17 millimeters for the top. Obviously, you're not going to be able to sketch a nice picture of the of the pyramids, but maybe you just want to at least have the scale copied down and simulate it kind of like that. So it's 17 millimeters, and that corresponds to 50 meters. And then if I measure the bottom here, I end up with, let's see here, 21 millimeters. So then what I can do is try to figure out the actual measurements on the pyramids. Let's just do it to start with. Let's do it in metric. We'll use meters to start with. So I'm going to measure one of the sides of the pyramid. So let's just say that I use this side of the pyramid here. Okay. And I'm going to measure that with my ruler to figure out what the size is on my picture. So on the picture that I'm viewing, this ends up being about 6 centimeters. Of course, that's 60 millimeters. Now, it's a little hard to see the pyramids. Anybody know why it's so washed out like that? Yeah, they have this thing in Egypt that we lack in Vancouver called the sun. They also don't have the greenery that helps to take away the glare when you look outside. So that's also the sand and everything else reflecting the sun off of the pyramids in the ground. But anyway, let's take a look then and try to figure out what the size of this pyramid would be. So if I have, 60 millimeters, and I want to get it into meters, there are 50 meters in my diagram for every 17 millimeters that we measured. So you probably recognize now where rates have come into this. It should look a lot like a rate problem to you. And I'll just cancel my units here. And I end up with, let's see here, 176 meters for that pyramid. Okay. So see if you can figure out how many feet are in how many feet that would be, and then I'll check my answer over with you. You're still going to use 60 meters or 60 millimeters again as your units. See if you can work out how many would go in if we used feet. right, so I'll take a look, see if you're on the right track here. Again, it's going to be a lot like the rate calculations we talked about last time. There's 60 millimeters on my picture. And in my diagram, there are 200 feet for every 21 millimeters. Which means if I cancel out my units, now I'm in feet. I end up with 571 feet. And again, if you've forgotten how the rate multiplication goes, you multiply on the top and you divide by the bottom. So before we go and talk about this, how accurate do you think this measurement could be? Or do you think there could be some problems with that measurement? What problems do you think could come up? Well, we all nod our heads thinking there's a problem, but, well, you might have made a miscalculation for sure. But even if I did all the math right, what might make the scale, off by a bit? Yeah, my measurement, when I use my ruler, it doesn't take much to be off by a couple millimeters. Maybe this is actually 57, or maybe this is 63. It's very hard to tell, and a few millimeters on that picture add up to like 20 feet on the actual diagram, right? It's a big mistake if you go off by a little bit in your measurement. So, when you do this, you probably want to just keep that in mind, right? I mean, I wouldn't go building maybe a rocket or something that's very technical off of something like Google Earth. But the other thing, of course, is Google Earth satellite is like way, way, way up in the sky. And the pictures that they're taking, well, they're actually rendered a little bit by the computer as well, because the Earth is curved and there's all kinds of things it does to try to make it look like the aerial view that you see. So we're going to try this again. Same idea. I'll measure it off for you with my ruler, and I want to see if you guys can work it out for Niagara Falls. So Niagara Falls, it's hard to sort of see in the diagram. The water is spilling over this way. It took me I don't know if I want to admit this, but it literally took me like 5 minutes to figure out the orientation of this picture. But the water is going over that way, and I believe the Canadian side is the left of your picture and the American side is the right. So it's actually probably, this came exactly off Google Earth, but it's probably upside down, because from what I picture anyways, I think Niagara Falls, that horseshoe faces south, but anyways, yeah. No, it faces north? Oh, okay.
The river flows south to north.
That's right, that makes sense. Okay, there we go, we got an expert here. So I'll measure off for you. Let's just take our, make a line along our diagram, and we'll say this is the width that we're going to use from this point across to this point. And that is going to end up being, say, 54 millimeters. Okay. So I'm going to give you guys a minute. I'll come around and see how you're doing with it, but see if you can convert that then into feet and meters. Okay, sorry, my fault. I forgot that you guys can't read this scale from the back of the theater. So this scale here on top, this is 21 millimeters. And the scale on the bottom is 13 millimeters. All right, so let me walk you guys through it. It looks like most people have the hang of it, so let's move on. We got 54 millimeters in our measurement, and there are 21 millimeters in 100 meters. Yeah, so we got 257 meters here. For the other one, we have 54 millimeters, and it says that there's 13 millimeters in 200 feet. So what did we end up with in feet this time? 830? 831 feet. And again, your diagram may vary, so depending on your accuracy, your measurement, but that's how we would use the scale to figure out the actual sizes. Okay. So now we're going to try doing an enlargement this time, which is that we're going to take a look at blood cells. So this is an actual picture of blood cells. They're not, the blood cells you're seeing have been dyed so that way you could actually see them. So for example, in green, that's actually a white blood cell. I don't know why they didn't just leave it white. But in green, that's a white blood cell. The purple are platelets. The red are red blood cells. And the gold and orangey kind of looking thing, I don't know what it is, but it's called a monocyte. So if you're a biology person, those are the actual pictures. Let's figure out the size of them. So from what I could gather of information here, the average red blood cell is 7 micrometers. Okay, so let's... There, I'll highlight this part of it. So in my picture, I can see, this is probably a good one to choose here because it's facing me pretty much head on. So I'll pick that one as my measurement for a red blood cell. Whoops. Because I don't have any sense of scale right now unless I connect it to the blood cell in the picture. So if I was to measure straight across here, I end up with, I'll show you the measurement I'm taking of it. So if I went straight across here, that's about 20, let's say 22 millimeters.
Do we have to measure ourselves when we do this?
Sorry?
Do we have to measure ourselves?
Yeah, so I mean, you guys, I'm projecting this up on a theater screen, so if you guys were sitting down doing your work, you'd need your ruler to put it onto the textbook or onto the question. But yeah, you'd have to do your own measurement. I'm assuming you guys can handle that. So, okay, 22 millimeters is the width there I've just measured. So let's try to figure out how big the platelets are and how big a monocyte is, that sort of thing. So before we do that, we have to, 22 millimeters gives us some sense of the picture. We can come up with a rate, and I'm just going to write that down here. The rate that we have is that in the picture, we have 22 millimeters. Oops, excuse me. We have 22 millimeters, and the thing is that in the problem, we're working with meters. So before we can do this, we need to convert 22 millimeters into meters to keep the units together. So if we start with 22 millimeters, does anybody know how many millimeters are in a meter?
1,000.
1,000. Yeah, there's 1,000 millimeters in a meter. So that's how many meters that this picture is. So I'll just put that in my margin here. It's 0.022 meters. Okay, so yeah, there is I forgot a few zeros in here. It's going to change our picture around. If you guys could make a correction in your notes there, I'll have to change it in mine. I guess I did this too late at night, but there's actually that many meters. Yeah, so there's actually 5 zeros. So from this, we can try to work out the scale of this diagram. So the scale that we have in our diagram, for every 0.0007 meters, there is 0.022. Which gives me a scale factor of 0.00032. I'll round it there. So what this means is that for every meter you give me, I'm going to multiply it by 0.00032. So whatever goes in gets multiplied by that scale factor so that it can be drawn in the right proportion on the diagram. So for example, if we calculated a scale factor of 10, that means before you put it in the diagram, you're going to multiply it by 10. Okay. All right, so let's try to figure out then, if I take one of these measurements, let's take a look at the a platelet. I'll measure across one of the platelets. And I get 8 millimeters there. So then to figure out the platelet that we've got, what I can do is start like we normally do. We've got 8 millimeters in the picture. And what we found out was that we have meters are the common unit here. So for 8 millimeters, there are 1,000 millimeters in 1 meter. Now I'm lined up to all the other measurements I have. So this is a measurement now that's being taken in millimeters, or sorry, in meters. And I can use that to write in the scale. So to get from, here's the way you want to think of the what you've got. This is your measurement here. So I'm going to call this capital M for a measurement. And I'm going to put A for the actual size. So our units are in the measurement on the diagram, but we want to get our units into the measurements that are actually there. So there are actually this many for the actual amount, or sorry, and the measurement that we got when we did it was 0.022. Okay. So that way my units, maybe I'll write this just a little bit over so you can see it a bit neater. This would be 8 millimeters, and this is the measurement. So my measurement off the diagram is gone, and I'm left with just the actual amount. Okay? So that's how you know which way the fraction is going to go, is you want to get into the actual amount. So the actual amount is on top. How much you measured off the diagram is what you want to cancel out, so it goes on the bottom. Now I know this is a step further, so we are going to practice this some more, so just bear with me while we try it a couple more times. Okay? What you'll notice is this fraction that we just came up with, that corresponds with this one up here. Okay. So if I multiplied it through, I can figure out how big a platelet cell should be. So let's see here, that would be 8 divided by 1,000 times 0.23457 and divided by 0.022. So I end up with 0.123455 0.025 meters. Okay. So what do you guys want to try then? A myocyte or a white blood cell? White blood cell? Okay, so the white blood cell, which in fact is green in this picture. I know. And again, I don't know if I should admit this either, but it took me like 5 minutes to find the white blood cell because it was green. But anyway, so let's just say this is where I'm going to measure across. And I look in my picture, and when I measure across there, I end up with about 23 millimeters. And you're not going to be able to see it there, so I'll put the 23 millimeters when I measured it off. So now I'm going to walk you through the conversion one more time, and I'll show you how we can get it into the actual measurement. So we have 23 millimeters, and this is measured. There is 1 meter in every 1,000 millimeters. And according to the diagram, there's 0.07 meters for every 0.022 meters that we measured. So the reason I'm saying that to you about measured and actual is it still works out like a rate. We start in millimeters, but millimeters are gone. The only thing I'm left with for my units is meters. We started with a measurement that we took off the ruler. Measured cancels out, and I'm left with the actual size. So that's how I knew which way the fraction was going to go. If I did it the other way around, it would be in the wrong units because actual would have been on the bottom. And I would have not everything would have canceled out properly. Okay, so this would be if I plugged it into the calculator. I'm pretty close to the red blood cell. So 732 meters, or 7.32 micrometers. So I'm going to leave you with the last one to try on your own. I'll measure it off the diagram and see if you can do the conversion properly. The last one that we needed to work with here is the myocyte. Does anybody know what that does? It's what? A type of white blood cell? Okay. Yay, science teachers. They did something good here, because I don't know what it is, but clearly you guys do. So let's just say here is our measurement across the myocyte. And my ruler says this is about, I'm going to take this as 16.5. So in this one here, it would be 16.5 millimeters. So see if you can walk through the calculation to figure out the actual size. And I want you to write out all your units. You need to get in the habit of doing this in rates to help cancel things out and see that you've properly set it up. So even if you think you understand how to do it, take the extra time, set up your units, and watch them cancel properly, because if your units cancel properly, then you've done the conversion right. That's basically the easiest way to check that you've done it correctly. All right, so the final one that we're going to work on, I'm running out of some room here, but I'll put my answer down here. I start with 16.5 millimeters, and again, I'm just going to leave it as a capital M since I'm running out of room for the measurement. And there's 1 meter in every 1,000 millimeters. And the last thing I have is that there's 7 micrometers in the actual measurement, and 0.022 meters in what I measured. So now when I go across, millimeters are gone, meters canceled out, so my final units are going to be meters, and I went from a measured value into the actual value. So the actual value, I believe, is going to be, this is what came up on some people's calculator. Can someone just verify this with me? Is that what you saw? So if that's the case, it's actually going to be 4 zeros. Oh, it was to the negative 6? Okay. So the way you interpret that as a decimal, I'll show you one of the tricks that people do. So one thing that I do is, this is the way I guess when you're in grade 9, if you would have done this with me, and I go 1, 2, 3, 4, 5, 6. That's how far away the decimal got moved from where it started. So at 5.25, I need to move it 1, 2, 3, 4, 5, 6. The decimal would be there. And that's how it would go into just a regular decimal. The other thing is that this being a 6, it will appear in the 6th place. So there's 1, 2, 3, 4, 5, and then the 6th place there is where I find the 5. So I don't have I'm not familiar with everyone's calculator, but usually you can change the mode so that it displays it as a decimal. But if you were to answer in a test or a worksheet, either is fine. You can answer either way. Okay, so I want to leave one with you guys to try right from the very beginning. Sorry, can I move that, or do people want a second to copy it down? I can move it? Okay. So here's something that's probably more practical for you guys to think about. I did this when I moved into my first apartment because I had to figure out where I could put all my furniture. Believe me, when you want to move, you want to do it as efficiently as possible because moving's no fun. So you want to know where everything's going to go. You want to be able to fit things in. So usually you'll take a quick sketch of the room, take some measurements, and try to figure out where you can place things. And for this one, if we have the apartment shown is drawn using a scale factor of 0.005, what are the actual dimensions of the room? So for example, with a scale factor of 0.005, that means if we start with, for example, let's say we started with 10 meters in real life. Then that means we would have 0.05 meters in the diagram. Okay, so if you know the scale factor is 0.005, that means you take real life measurement and you multiply by the scale factor to find out how big it'll be in your diagram. So I'm going to let you guys try to work it out, but what I want to know is what are the dimensions, the actual dimensions for these rooms, if that's how big it is on your sheet. Okay, so here's the rate you should be thinking of. I've got 2 centimeters. And I'm going to use D for diagram. I have 2 centimeters in the diagram. And I'm going to multiply that by the scale factor. You notice there's no units. You could convert it to meters and talk about meters. But it also applies to a centimeter. 1 centimeter in the diagram is 0.005 centimeters in, 1 centimeter in real life is 0.005 centimeters in the diagram. So I'm going to write that down. 1 centimeter in the real world, the actual measurement, is 0.005 in the diagram. So where should it go? Where should 1 and 0.05 go? Top or bottom? Who goes where? You got a 50-50 shot even if you don't know what's going on. Yeah, so it goes to the top, 1 centimeter, the actual measurement, and 0.05 centimeters from the diagram, because then when I look at my units, centimeters are gone there, the diagram is gone, I'm left with 1 actual centimeter. So this is the actual size of the measurement. So that gives me 400 centimeters, and for those of you who did it in meters, that's fine, or you'd have 4 meters. So you've already done the calculation for 4 meters, actually not a bad size for a room, that's like 10 feet. But anyways, you've already done the 2, so we can check off a lot of these measurements. The only other ones we need to work out are what's 2.5 centimeters and what's 2.4 centimeters. So again, walk yourself through the units and actually watch them cancel out, and then we'll go over them together. All right, so unfortunately my page is filled right in, so I'm going to erase my old calculations so that we can do the other 2. So I need to figure out what 2.5 centimeters is. It's this room here that has 2.5 centimeters. So 2.5 centimeters in the diagram, and 1 centimeter is 0.005 in the diagram. So centimeters are gone. The diagram's no longer in my problem, and I have 1 actual my units are going to be in actual centimeters. So if I use my calculator here, oops, it's going to be, what, 500? Or about 5 meters. Okay, and then the last one that we need to do is 2.4 in the living room. So, why did I, sorry?
No, we're looking for 2.5.
We've already found 2 centimeters, so the only ones I need to work out in the diagram now are 2.5 and 2.4. So 2.4 centimeters in the diagram. 1 centimeter in the actual world is going to be 0.05 in the diagram.
We will have a test.
So this is going to be 480 centimeters, or 4.8 meters. So for example, I could tell you this, the living room here is 2.4 by 2, but that's the same thing as 4.8 meters by 4 meters.
It doesn't say which unit we say it.
You could say 480 centimeters by 400 centimeters as well. Unless it specifically was to ask you for a certain unit, then you'd have to use that certain unit, okay? But it'll be clear if you're being graded on it. I'll make sure it says the units I'm asking for. Okay. All right, so there's can I move this down now?
Yeah.
Okay. Yeah, so Johnson Heights. Yeah, you can tell the picture's old because we no longer have this part of the school. That one's gone because of the construction. But anyway,
No, just the pyramid.
we're going to try to use the diagram to figure out the scale factor. So let's walk through this here, and I'll show you how this goes because I'm going to ask you to do something similar for your homework. What's the area that Johnson Heights sits on? This is 20 meters on top, and this is 100 feet on the bottom. So if I was to take a measurement and go right across the school, let's just count the grass as the property. So if there's no grass on it, then we won't count it. But it goes all the way across. And and say these are going to be the measurements that I take for the width and the height of the property that Johnson Heights sits on.
I thought there's no grass. Oh.
Okay, so let's measure them out. This is, whoops. This is 12 centimeters up to here. My ruler is not quite long enough, but, and then that gives me another, let's see here, 18. Sorry, no, 28. So this would be 148 millimeters. And the height of this diagram here would be 53 millimeters. All right. If I look on the diagram here, the top line is going to be 12.5 millimeters. And the bottom line is going to be, let's see here, let's say 19.5. So refresh my memory here, if we just call this a rectangle, how do you find the area of a rectangle?
Length times.
Yeah, it's just going to be length times width. So that's what I'm going to use here, is I'm going to use the length times the width. So go ahead and figure out what's the actual length of the property, what's the actual width of the property, using the scale. Okay, so it sounds like you guys have gotten through it, so I'm going to work through my calculations. 53 millimeters in the diagram is worth, let's see here, 12.5 millimeters, and that's 20 meters. Now again, if you want to connect what we were doing before, this is in the diagram, this is in the diagram, this is the actual amount. So the diagram is gone, I'm left with the actual measurement. And millimeters is out, I'm into meters now. So that'll give me the length of the property, sorry, the width of the property or height. 53 times 20. So I end up with 84.8 meters. And if I want to know the length of our property, it goes 12.5 millimeters is worth 20 meters. So I get 236.8 meters. And if I put those two together, $84.8 times 236.8, I get 20,080 meters. So if we looked in this diagram and someone asked us to find the scale factor, we could do that with the information that we've got here. And I'll show you how we can do that. So the scale diagram, the way that works, sorry, the scale factor, remember, is, let's just say we took 1 meter in real life. It's going to be how much in the diagram. So the way we figure that out is we can say what we measured Okay, so I'm going to use the ones that are given. The ones that are given is 20 meters in real life. Is going to become, 12.5 millimeters in the diagram. And the way I got that information was right off of the scale that appears on the map. So the way we could work it out then, what happens to 20 meters is 12.5 millimeters becomes 20 and I have 1 meter has 1,000 millimeters. So now that my units are gone, this is the ratio that I get out of this diagram. So in this picture, the scale factor is 0.00625. It's making it quite small. If you give me 1 meter in the real world, I have to cut it down to 0.000625 on this chart. Okay. So when you're looking for the scale factor, it'd probably be helpful to write that down. Scale factor, and your textbook uses the letter K, is going to be equal to the diagram divided by real life. And you must have matching units. So all I want to show you here, and just for the sake of time, if we were to go and measure this out using the scale factor, it's tempting to just say that, let's see here, we want to find the area, but the area, if we can do this with the scale, it's just that there's this little change here. It's not just the scale factor, it's the scale factor squared. And the reason why is the scale factor is used twice. Once when you multiply by the length and once when you multiply by the width. So because you're multiplying by the scale factor twice, if you calculate the area, you actually end up with the scale factor squared. So I could do it in this picture. Let me show you how it would look if we did it in the picture. Here's my, I have 53 and 148. So 53 millimeters and 148. That gives me the area in millimeters, not quite just off the diagram. So I get 7,844 millimeters, or 7.844 meters squared. So the 53 by 148, that's in the diagram. So if I wanted to get this into the area, that's what I'm going to use is I start with 7.844 meters squared. And this is from the diagram. When I multiply, it says 1 meter in the real world is going to be 0.000625 in the diagram. And if I just did that one scale factor, the problem is when I multiply it out, you're going to get, let's see here, 7.844. Which is not the same as what we calculated. So that's why we need to use it twice. So I'm going to go and then say that's not the way this thing needs to be used. You have to use it twice. Once for the length and once for the width. So I'll put an L here for length and once for the width. Oh, and sorry, looking at looking at this, I'm off just slightly because I've made a classic mistake here. So my apologies, but this is actually not going to be that many meters squared. And I'll show you why that is here. Let me just do this in the margin. 7,844 millimeters squared. To get that into meters squared, you actually have to do it twice for the same reason that I'm trying to tell you. It's because we multiplied by it. So there's actually 2 millimeters. So when I go like this, I get rid of one of them, then I get rid of the other. That puts me into meters squared there. So it's actually going to be that sounds better. It was sounding awfully large thinking about that diagram having that many meters. Because it's a computer screen. That would be a 7.844 meter squared computer screen that I'm writing on, which should have told me that I had a mistake there. So after I multiply this through, I end up with 20,080. So anyways, my apologies there. The key thing here is you have to do it twice. Once because you multiplied by the length, and then once because you multiplied by the width. All right, so I did have something else I wanted to just go over, but let's stop here.